LINT tools do not understand design intent. They rely entirely on how accurately the design is configured through top module selection, file lists, include paths, macros, and language settings. A correct setup ensures that reported violations reflect real design issues rather than false errors caused by misconfiguration. This walkthrough is based on practical industry experience, focusing on how proper setup directly impacts productivity, debug efficiency, and design confidence. These elements collectively define how the LINT tool understands the design hierarchy, compilation context, and analysis intent. Providing the correct RTL files, paths, macros, top module, libraries, and rule deck ensures that LINT analyzes the real design behavior and reports only meaningful violations. Here we are walking through very basic and day-to-day setup requirement. You note this directory structure separates design sources, verification files, tool execution data, automation scripts, and generated reports to keep the LINT flow clean and manageable. A well-organized project structure improves reproducibility, simplifies debugging, and supports scalable team-based development. You know that we can go with GUI mode as you start, but I recommend script-based ahead. In GUI mode, you know we begin by launching spyglass and creating a new project to define the analysis workspace. Next, we add the RTL files and explicitly set the top module so the tool understands the design hierarchy. After selecting the appropriate LINT goal, such as start go synthesis, we run LINT and then interactively analyze the reported violations using the GUI to distinguish real issues from setup-related noise. This is a script-based LINT setup where the project file LINT PRJ defines the top module, language mode, RTL sources, include paths, and macros, then selects the LINT goal and runs the analysis. This is the recommended industry practice for executing LINT in a consistent and repeatable design flow. Similar to other popular LINT tools, Cadence JasperGold, SuperLINT, and HAL/LEC LINT flows also require complete and correct setup, including RTL files, include paths, defines, top module, and rule configuration to ensure accurate and meaningful LINT analysis. So remember, LINT is a static tool. It has no understanding of design intent. If the setup is wrong, the tool will misinterpret the design and flood us with false violations. That's why getting the setup right is more important than fixing any single LINT error. Before looking for real design bugs, we first walk through the key setup checks that every designer should follow. The first thing to verify is the top module has an incorrect top module breaks the design hierarchy and leads to undriven ports, black boxed instances, unused signals, and a flood of false LINT violations. Followed by looking into missing include directory. If the include directory is missing, for example, forgetting set to optioning dir /RTL/include, the tool cannot find defined macros and parameter files, breaking conditional compilation and resulting in undeclared identifiers, with mismatches, and multiple syntax-related warnings. And so on, the synthesis macros are not defined, for example, missing set option define synthesis. The LINT tool enables the wrong code path, analyzes simulation only or test bench logic, and reports lat warnings, X assignments, and multiple driver violations that are not real design issues. Now imagine this: the design is written in system Verilog or VHDL, but the language mode is set to Verilog. Suddenly, the tool starts misunderstanding logic types, ignores always COM, breaks interfaces, and begins reporting latches and port mismatches that don't actually exist. If the language mode is set incorrectly, such as using Verilog for system Verilog design, the LINT tool misinterprets logic types, fails to understand always COM and interfaces, and generates false latch inferences and port mismatch errors. This checklist summarizes the essential setup items that must be verified before searching for real design bugs, confirming the correct top module, inclusion of all RTL files, proper include paths and defines, correct system Verilog language mode, appropriate goal selection, linked libraries, and ensuring no test bench files are included so that the LINT tool analyzes the correct design and reports only meaningful violation. This structured approach simplifies complex designs and aligns the LINT setup with the overall RTL quality objectives. This is the recommended industry best practice order for debugging a LINT environment. The process begins by checking the log file to quickly identify setup and tool-related issues, followed by verifying the top module, file list, defines, include paths, and language mode to ensure the tool is analyzing the design correctly. Black boxed instances are then reviewed to confirm that no RTL or libraries are missing. Only after all setup issues are resolved should designers analyze reported violations, ensuring that the remaining errors reflect real design problems rather than configuration mistakes. So, UV got the key message. Never start fixing RTL before validating the setup, because nearly 80% of large lint violation reports are caused by setup issues, not real design bugs. Up next, we will explore RTL lint rule categories, DFT lint, and low power lint, before moving into part 2, which focuses on advanced and specific lint setup scenarios. This knowledge sharing initiative is powered by https://fpgeekengineers.com, driven by a team of ASIC and FPGA experts.